What happens to the current in the circuit to the right? The sum of the currents through each of the resistors equals the current in the battery. Let's see why that makes sense. We've got the current coming out of here, which is just a whole bunch of charges. Then the charges split up here. Some go this way, some go that way. And then they recombine over here, and they come back to the negative terminal of the battery. So whatever comes in has to come out, right? You're not going to lose any charges in the resistors. They keep moving through. So we have the current coming out of the battery, which is I, has to equal the current going through each of the resistors, and you add them up. So here's I1, here's I1, and here is I2. So I equals I1 plus I2. What happens to the voltage as the charges move around the circuit? The voltage across each resistor is going to be the same. And why is that? Okay, let's look. The battery gives a volt per coulomb for every group of charges, or the same energy for every charge that comes out of here. Okay, and that level, we call it V. That's the voltage they get. That's the energy per charge. On the other side, right over here, that's connected to the negative terminal of the battery, which we say is at 0 volts, so that the voltage drop across the battery is V. So if this side of the resistors is V, this side is 0 volts, what does that mean? Charges, whether they go through the top or the bottom, will drop the same voltage. So now we have V, which is the voltage from the battery, is equal to V1 and V2. Separately, V equals V1 equals V2. Can you see how this is the reverse of what we did for the series circuit? Please feel free to go back and check out the slides and see how the assumptions there were just the opposite of what we have for parallel circuits. We'll start, and let's see, we're going to do it for 3 different resistors here. And the total current is equal to the current through each one of them, I1 plus I2 plus I3. Now what is I equal to according to Ohm's law? Well, V over R. So we substitute in, and you do the subscripts for each of the individual resistors. And what did we say on the previous slide? That V is equal to V1 and V2, and it also equals V3. So we don't need the subscripts anymore. They're all the same voltage, so we put V in for all the different voltages. We can certainly factor V out at this time, because every one of the guys here has a V in the numerator. Divide by V, and you get 1 over R equivalent equals 1 over R1 plus 1 over R2 plus 1 over R3. Now be careful when you calculate this. A lot of times you'll do all of this work here and then forget to take its inverse, because when you do this you have found 1 over R equivalent, but you need to find R equivalent. What happens to the equivalent resistance if you add more resistors in parallel? Adding more resistors in parallel is the opposite of series. In this case, the equivalent resistance will actually decrease. So by adding more resistors, maybe intuitively you thought that would increase the resistance, but in parallel it decreases it. Go ahead and check the math out with some examples and you'll see it's true. Obviously that's not a proof of it, but it's pretty good. You won't find any cases where that doesn't work. Now conceptually, why does this work? What you have now are more paths for the electrons to flow, right? If you just had 2 in parallel, looks like a heart monitor there, don't mean that. The charges have to either go through here or here. When you add another resistor, they have another path to go through. And then you add another resistor, yet another path. So for a given electric potential, you have more current flowing, and that means you have a smaller resistance. There's more room for these charges to go. Another analogy is if you have a bunch of people in a room and there's one door, it's going to take a certain amount of time to get them all out of the room. But if you now have 10 doors, it goes much, much quicker. So it's the same kind of thing here.